Now, any question on this, on these Bell inequalities? In fact, it's nice that, I mean, in a sense, without knowing what the underlying theory might be, we can just eliminate some of the theories. Which if the theory makes a claim that the result of the measurement is determined before the measurement by some mechanism, by some means, etc., then these inequalities should hold, and we know from experiment that they do not hold. So that basically, in a sense, proves almost that the outcome of the measurement is not determined before we make the measurement. So it's only determined when we make the measurement. It's also crucial, at least in the quantum mechanical test, in the experimental tests, that these coordinates, these axes A, B, and C, they shouldn't all be orthogonal to each other. If you choose the X, Y, Z axis, for example, 3 orthogonal axes as A, B, C, then, I mean, the experiment doesn't violate the Bell's inequalities. Well, if you just choose 3 axes, they are linearly dependent, then you have the violation of the Bell's inequality. Okay, after this interlude, let's say, back to rotations. So, now, we will define some operators. Now, if you consider, when we had these generators of rotation, Ji, Jk, we had seen that it is I just times epsilon I, Jk. And then the expectation values of these Ji's, we had also calculated in an arbitrary kit the expectation values. They are written in this form. So R is our 3-dimensional rotation matrix. And so this basically tells me that the expectation values of J's, they just behave like ordinary 3-dimensional vectors. And to prove this relation, if you remember, the only thing we used was this commutation relation. We didn't use anything else. It was enough that we know this commutation relation. And, well, let's do one thing else. Let's consider 3 other operators. Vi. And let's also assume that these 3 operators, they satisfy almost exactly the same commutation relation. Vk. It just looks like the commutation relation between the rotation generators. The commutator of V with J gives us some other component of V. And let's look at how the expectation value of Vx changes under rotations. Well, this is equal to alpha V alpha, this time is the rotated alpha. These rotation operators, the rotated kits, we can just write as D acting on them. And for simplicity, let's just assume a rotation around the z-axis by an angle theta. So these operators will be alpha e to power I over h bar theta jz Vx e to power minus I over h bar theta jz. Now we need to calculate this matrix. We already know the Baker-Hausdorff formula. This is equal to Vx plus I over h bar theta jz Vx plus I over h bar theta squared jz Vx etc. Well, you see Jz Vx, this is equal to minus Vx Jz, which is minus I h bar epsilon xz k Vk. But k has to be y, the only non-zero component. This is minus I h bar epsilon 132 Vy. Well, this is minus 1 I h bar Vy. Jz. Now this is the first term over here. Well, if you look at the second term contains one more commutator. This is equal to I h bar Jz Vy, which is equal to minus I h bar Vy Jz. This is equal to minus I h bar times I h bar Vx. So you start with Vx, one commutator, it becomes Vy, another commutator, it becomes Vx, or it just goes Vx, Vy, Vx, Vy. So basically that operator this is Vx. Well, the second term has I over h bar theta times the commutator, which we had evaluated to be I h bar Vy. The third term has I over h bar theta squared times h bar squared Vx, etc. And if you calculate all the terms, what you would end up having is, this is Vx, 1 minus theta squared. Well, here I have a 1 over 2 factorial, which I also forgot here. Minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, etc. And then we have the second term is minus theta, if we just keep calculating, is theta cubed over 3 factorial, now minus theta cubed over 3 factorial, plus theta to the 5 over 5 factorial, etc. Vy. So this is Vx cosine theta minus Vy sine theta, which basically tells me that the expectation value of Vx under rotation, it is just Vx cosine theta, expectation value of Vx cosine theta minus Vy sine theta. Now the components, the expectation values of this operator V just rotate like an ordinary vector. And hence in general you can just write it as the V, or under rotation the expectation value of the I component is just Rij, the expectation value of the J component. Well, so you see, we don't know what this operator V is. We don't need to know to say that it transforms as a vector operator. The only thing we need is this commutation relation. No, sorry, not that one. Is this one. So any three operators that satisfy this commutation relation are called vector operators. Well, the reason of the name is kind of obvious. They just transform like a vector. So that's why we call them vector operators. Well, in classical mechanics, we have vectors and we also have their generalization. We have also tensors. So we can talk about some tensors in quantum mechanics also. Let's say that we have, or in fact, before going to tensors, let's look at these commutation relations a bit in more detail. Now, let's look at the commutator of Vx plus I Vy with Jz. Well, this will be I h bar epsilon 1. Now, let me write. This is Vx Vz plus I Vy Vz, which is equal to, no, sorry, Jz. Well, the commutator of Vx Vz is minus I h bar Vy plus I. The commutator of Vy with Jz is I h bar Vx. So this is minus h bar Vx plus I Vy. So that tells me that Vx plus I Vy, commutator with Jz, is equal to minus h bar Vx plus I Vy. Now you can just repeat the same derivation with the upper sign. The other sign, Vx minus I Vy Jz, will be equal to plus h bar Vx minus I Vy. Now most of the time we define these operators as V plus minus. This is Vx plus or minus I Vy. And then, of course, Vz multiplying Jz, this is equal to 0. We will see. Well, let's look at what happens to Jz, to the eigenvalue of Jz, for, let's say, we start with an operator with a ket Jm and act on it with V plus. I repeat, we don't know what this V plus is. It's just some operator which satisfies that commutation relation. Well, this will be equal to V plus Jz plus Jz V plus minus V plus Jz, acting on the same ket. I just added and subtracted V plus Jz. Well, the commutation relation just tells me that this is h bar V plus. So this is equal to V plus Jz plus h bar V plus acting on J and M. Well, I know how Jz acts. This is nothing but h bar M plus 1 Jm. So Jz acting on V plus Jm has an eigenvalue which has M increased by 1. So this new ket that I obtained by acting on a ket with an eigenvalue M is still an eigenvalue of Jz with eigenvalue M plus 1. In a way, V plus is like, I'm not saying exactly equal to, but it's similar to some state with the m component plus 1. I'm saying they are not equal to. You see, if I take one ket with the z component of angular momentum plus 1, and if you just consider, for example, two particles, one has z component of angular momentum plus 1, the other one has the z component of angular momentum m. If you take their product, you obtain a state that has a z component of angular momentum m plus 1. So this relation over here is just like that. In that sense, V plus is like a ket which has the m value plus 1. And if you do the same thing with the V minus, you get the other side. For example, from this argument, straight away you can say that V plus minus Jm is equal to 0. Again, I repeat, I don't know what these V operators are. I have no idea. They can be any V operator as long as they satisfy the commutation relation. But nevertheless, I know that their expectation value in a state that has a definite value of J and M, it should be 0. Because you see, this product is an eigenket of Jz with an eigenvalue different than H bar M. So if you have two kets that have different eigenvalues, then they are orthogonal to each other. So that's why I know that this matrix element is automatically 0. This can be, for example, these V operators, the vector operators can be the position operators, for example. And then V operator can be, V is the position, and so this will be, for example, when you are studying the hydrogen atom in an electric field. The coupling of the electric field to the electron will be the electric field multiplied by the position of the electron. Position operator of the electron is a vector operator. So if you just, you take V can be the position, you consider the plus minus components, then their matrix elements will be 0. And the non-zero matrix elements, by the way, will be only, well, even this J can be J prime. J prime, M prime, M plus minus 1, V plus minus J, M. These will be non-zero in general. Either you take the above signs in both of them or the below signs in both of them. Now, the next thing will be the generalization of vector operators, so-called, let's say, the tensor operators. Now, for example, in classical physics, the one simple example of a tensor operator is you take two vector operators, let's say U and V. You take the I component of one of them and the J component of the other one. So this is a tensor. Let's call it Tij. And, well, how does it transform? Well, basically, we will do the same thing. You see Tij in the rotated basis will be equal to let me just do a couple of steps. This will be alpha d r dagger ui uj dr alpha. Here I just insert dr d dagger r because this is 1. But then you see this is nothing but Rij and this is nothing but let me call this K. Rjlul V. So this is equal to Rik RJL, the expectation value of UK VL. RIK RJL, the expectation value of TKL. This is our tensor operator. In each one of the indices, it just transforms like a vector. Now let me look at a couple of things. Let me just multiply both sides by Kronecker delta ij. Well, the left-hand side just becomes ui vi under rotations. This is equal to R transpose, the ki element, times RIL TKL ui vi. Well, the left-hand side is nothing but the scalar product of these two operators, u dot v. I have these two vector operators, I take their scalar product and rotate. The right-hand side becomes R transpose R K and L. But these rotation matrices in 3 dimensions, they are just orthogonal matrices. Their product, if you take the transpose of one and multiply with itself, is just 1. So this is Kronecker delta KL, TKL. So U dot V, expectation value under rotations, this is just expectation value of U dot V. Well, you see there are these Tij's, as you can also write it as a 3 by 3 matrix. There are 9 elements in that matrix, but one of them, which corresponds to U dot V, does not change under rotations. Well, something that doesn't change under rotations is what we call a scalar. Let me look at something else. Let me look at Tij minus Tji. Now, the reason why I look at that combination is that that combination is anti-symmetric under the exchange of I and j. That's why I'm considering that one. Well, this will be equal to Rik, Rjl, Tkl. This is how the first term transforms under rotations, minus Rjk, Ril, Tkl. This is how the second term transforms under rotations. In the second term, I'll just exchange the positions of j and k, j and I. Now I will do a trick. You see, the k and l in the second term, in the second line, they are just summed over. They are dummy indices. I can just give them whichever name I want. I will just name k as l and l as k. So under rotation, this difference just becomes Rik Rjl Tkl minus Tlk. How many matrices do I have? Let me just define it. How many independent terms does Aij have? You see, I and j, they take 3 possible values, so I can write this Aij as a 3 by 3 matrix. But it's anti-symmetric. That automatically tells me that the diagonal entries are all 0. Here I have 3 entries. The lower 3, they are just the negatives of the upper 3. So here I have 3 independent numbers that tell me what these Aij's are. And under rotation, they just go mix among themselves. In fact, I can also write this Tij minus Tji as epsilon ijk, let's say Vk, V being some vector operator. So a vector has 3 components, this Aij has 3 components. And finally, if you just look at Tij plus Tji minus 1/3 Kronecker delta Ij Tkk, under rotations, the matrix element of this operator also becomes Ril Rjm Tlm plus Tml minus 1/3 Kronecker delta Ml Tpp. So what did I do? I started with Ui, Uj, Vj. I can write this Ui, Vj as 1/2 Ui, Vj minus Uj, Vi plus 1/2 Ui, Vj plus Ui, Vj minus 1/3 Kronecker delta Ij Uk, Vk plus 1/6 Kronecker delta Ij U dot V. Now, the reason why I have such a weird combination over here is that if you take that combination, multiply it with Kronecker delta Ij, this is 2/3, sorry. This is 0. Well, basically, this is called the trace of my tensor. This is called the anti-symmetric component of my tensor, and this is called the traceless symmetric component of my tensor. And what we had seen is that under rotations, every line in this expression gets mixed up among themselves. The first line doesn't get mixed up with the second line. The second line does not get mixed up with the third line, etc. So just all the terms in each one of those lines get mixed up among themselves. Like if you look at the vectors, how we call a vector. A vector is some 3 numbers, let's say, that get mixed up under rotations in a particular way. So these things, and there's no 4th thing or the 5th thing that gets mixed up in this set, let's say. Similarly, here we have these 3 things that get mixed up. Now, if you just count how many independent variables we have in each one of these sets, here we have 3 independent variables in the first line. In the last line, we have 1 independent variable. It's just u.v. And in this line, we have 5 independent variables. Well, let's see. If we have a spin 1 state, and if you have a spin 1 system and another spin 1 system, when we combine them, we obtain a total spin 2 system, total angular momentum 2 system. We had already seen that L, the total angular momentum, or J, if we add 2 angular momentums, it's less than the sum and larger than or equal to the difference. So if we have J is equal to 1, another system with J is equal to 2, when we put them together, we can obtain total J is equal to 2, or total J is equal to 1, total J is equal to 0. Well, a state that has a total J is equal to 2 has 5 different states. A system that has a total J is equal to 1, we have 3 different states, and a system that has a total J is equal to 0 has just a single state, 5, 3, 1. Well, in that sense also, what we use these, when we call these are vector operators, we also say that they are L is equal to 1 operators. If we just multiply 2 L equal to 1 operators, let me go back, I didn't write it explicitly over here, but V plus minus, they are similar to this one. And Vz, since it doesn't change the Z component, it's just like this kit. Now, if you just keep that analogy, well, this separation kind of also starts to make sense. You see, you have 2 angular momentum 1 objects, let's say, let's not call them kits, they are not kits. 2 objects, we give them some angular momentum and we call them angular momentum 1. If we multiply 2 of angular momentum 1 objects, we get objects which have a total angular momentum 2, 5 of them. We get objects which have angular momentum 1, again 5 of them. And we get objects which have angular momentum 0, again 5 of them, 1 of them, sorry, 5, 3, and 1. In a sense, this is just kind of our generalization of our kits to operate. What we had done in kits, we can basically do it the same thing with operators. Now the question, there are a couple of questions over here. One of them is, well, we had already seen that if you start with J is equal to 1, J is equal to 1 operators, by multiplying them we get some new operators, but they are so-called reducible. You see, this product of the components of 2 vector operators is reducible in the sense that I can break it apart into sum of terms that just mix among themselves. And these representations over here, these ones on the right-hand side, each one of those lines, they are called irreducible tensor operators. These are reducible. These are irreducible. Well, of course, okay, here I didn't specify it before and I added afterwards. How can we tell that V is actually L is equal to 1? A vector operator is L is equal to 1. You see, in the case of a kit, that's kind of easy. You act on the kit by J squared, and if you get H bar squared L or J is equal to 1, J plus 1 alpha, this tells me that alpha has J is equal to 1, or J has J. So in the case of kits, this was how we identified the J quantum number. Now what about the operators? Well, let's look at some more commutation relations. Maybe they might give us some idea. One, you see, when we looked at these commutation relations, for vector operators, we had j plus minus, jz, commutating with v plus minus. This was just h bar plus minus h bar v plus minus. Jz commuted with vz. So like the action of an operator on the kits, it just looks like the commutation relation. Yeah, you see this is analogous to Jz acting on plus minus 1. This is equal to plus minus h bar plus minus 1. This is analogous to Jz acting on 0. It's just 0. So in analogy, it just looks like the action of the angular momentum on operators is their commutator. So let's look at the commutator of j squared with, which one would you like? Well, let's try with Vz. Well, this is equal to, well, let's just say Vi. This is equal to Jj squared commutator with Vi. This is equal to Jz, Jj Vi plus Jj Vi multiplied with Jj. This is equal to Jj minus I h bar epsilon I j k vk minus I h bar epsilon I j k vk jj. This is minus I h bar epsilon I j k jj vk minus vk jj. Plus. Yeah, not so illuminating. So one problem is that we have j operators on the right-hand side. I don't want the j operators on the right-hand side. But what we can do is, let's look at this one, jj. You see, j squared acting on my any kit is jj acting on jj acting on alpha. So again, just using our analogy, jj acting on alpha is analogous in the operator case. It's the commutator of jj with alpha, jj with vi. So this will be the analog action of j squared on this operator's v, not the other way around. Well, let's see what this will be. This is jj. That commutator is minus I h bar epsilon I j k vk, which is equal to minus I h bar epsilon I j k jj vk minus I h bar epsilon I j k, and that commutator is minus I h bar epsilon k j l v l. I have the product of two epsilons. This is minus h bar squared. Let's say epsilon I k j epsilon l j k v l What is this product? Twice Kronecker delta IL. So this is minus h bar squared 1, 1 plus 1, VI. So JJ VI is equal to, well, this minus looks weird, but minus h bar squared 1 times 1 plus 1 VI. So it's just like J is equal to 1. So I mean, if you identify the action of operator on the kets with the commutator of the J operator with the your vector operators, so then this V, the vector operators, they do correspond to J is equal to 1, and we have all these three, for L is equal to 1, we have the M is equal to plus minus 1 or 0. They are very analogous. Mathematically speaking, they behave identically. But that also tells me that whatever I do in terms of the kets, I can also do with these operators. So one thing I did with the operators, with the kets, was, let's say if we start with J1, M1, if we multiply this with J2, M2, this was one basis. An alternative basis was J1, J2, J and M. The first basis, the so-called uncoupled basis in some books, they have the definite J1 squared, definite J2 squared, definite J1z, and definite J2z eigenvalues. The second eigenket has definite J1 squared and J2 squared. They also have the definite total J squared and the total Jz. And there is a correspondence between the two. They are both our bases. Since they are our bases, we should be able to write one in terms of the other one, and this we can just write as J1, J2, Jm, J1, M1, J2, M2, J1, M1, J2, M2. These are what we had defined the Clebsch-Gordon coefficients. Now, let me just define a general definition of the tensor operators. Now, let me just pick up the signs properly. Well, I will denote them by the QK. Well, what does this mean? K is like the M value, Q is like the, K is like the L value, Q is like the M value. And if I take the commutator of this thing with Jz, it should give me H bar Q, TQK. And if I take the commutator of them with J plus minus, well, the commutator is just like the action on the kets. And J plus minus, their action on the kets will be just K minus or plus Q, K plus or minus Q plus 1. These are what are defined as the tensor operators. Now you see, I'm just using the analogy between the kets and some kind of operators. And you see, since they don't get mixed, I mean, you see, J's commutator with j's, the various components, they don't mix the different k components. They only mix the various q components. It's just like, you see our vectors over here. We had seen explicitly that under rotation, the operators in the first row, they just mixed up among themselves. The operators in the second row, they get mixed up among themselves. And the operators on the third row, they get, well, that's just one. It doesn't mix with anything else. And this operator is q is equal to 0. This operator is k is equal to 0. This is k is equal to 1. This is k is equal to 2. So we have these three operators already. And let's say you have an operator with k1, another operator with k2. One has q1, the other one has q2. You can multiply them. But of course, this product will not be reducible. Well, you can obtain the irreducible representation with total spin k. And q value, of course, q should be equal to q1 plus q2. And the coefficients appearing there will be nothing but our Clebsch-Gordon coefficients. K1, Q1, K2, Q2, K1, K2, KQ. Well, in your book there is an explicit proof that how this row, to prove that this is actually an operator that satisfies this relation, these relations, well, you have to just go ahead and calculate each one separately. And there is a proof in your book if you are interested. But basically, if you just keep the analogy with the kets and the operators, that is mathematical, they have these similar properties. Well, this is kind of obvious. Just the way you obtain multiply the kets is the same for the operators. Now, the interesting thing will be the matrix elements of these things. Now, the claim will be this one. Now, let me look at. I have some operator TQK, and I will be looking at this matrix elements, J prime, M prime. So I have some kind of a tensor operator, TQK. I'm looking at its matrix elements between two states. One has a J value J, the other one J and M value J M, the other one J prime and M prime. This alpha represents any other quantum number that the system can have. This will be equal to JK MQ JK J prime M prime alpha prime J prime TK alpha J. Okay, so what does all of this thing mean? You see, look at this matrix element. This is independent of M and M prime. And this thing over here is nothing but our Clebsch-Gordon coefficients. So all the M and M prime dependencies of such a matrix element, they are already incorporated in these Clebsch-Gordon coefficients. You don't need to calculate the matrix elements for various values of m and m prime. You just pick up one possible value of m and m prime, calculate that matrix element, and using this relation, obtain this matrix element, which is also sometimes called the reduced matrix element. And then we are done. You know all the matrix elements for all possible values of m and m prime. Just pick up one. If you calculate one of them, that is enough. And we are not assuming anything. The only thing we assume here is that TKQ is a tensor operator of rank K, has the value Q, and we are looking at its matrix element between two eigenkets of J squared and Jz. Whatever the system is, it can be an electron in the hydrogen atom or whatever you want, some nucleus, protons in the nucleus, etc. So this is the so-called Wigner-Eckardt theorem. Well, the proof is kind of, it looks complicated. The proof is kind of easier in the sense that, well, let me not go into the proof. You are already tired, I suppose. And at least I don't want you to finish this course without having heard of the Wigner-Eckardt theorem. Now you have heard that it exists. And well, the proof will not really tell you much about why this is important. But when you in your future studies, if you see such a theorem, you will know where to look. So basically, this Wigner-Eckardt theorem tells you that if you are looking for matrix elements of states with definite J and M, you don't have to calculate for all values of M. Calculate for one of them, and this Wigner-Eckardt theorem relates all the others to that single matrix element, single M value. Yes, last questions.